Problem the last. So, a projectile is launched horizontally from the top of a cliff. There are some givens that I have decided to write in this image, but first, let's get to the drawing. In honor of our catapult project, I decided to draw a catapult as being the launcher of this projectile. The height of the cliff is 20 meters, y is defined at 0 as the base of the cliff, and v1 is 10 meters per second, and this is perfectly horizontal, so perfectly straight in its first launch. A asked sketch the horizontal position, velocity, and acceleration as a function of time. So, first, the horizontal position. So, there are no forces acting on this velocity in the horizontal, which is completely horizontal. 10 meters per second is going purely horizontal, so that's going to stay constant. Which means that there's going to be an ever-increasing and ever-linearly increasing position away from the cliff for the delta x. And as I just said, the v and the x is going to remain constant since there are no forces acting on the v in any way to act against it. And that's something that we learned, I think, in Newton's first law, that an object is not going to slow down unless something acts upon it. And we're ignoring air resistance, so yes, there is truly nothing acting upon it until it hits the ground. Acceleration, the x, is going to be 0, because if there were any acceleration, then the v would not be constant. Now let's get to the vertical position, velocity, and acceleration. So the vertical position is going to start up top, and then ever increasingly, ever faster and faster, it's going to speed up going down. And that's because the vertical acceleration is negative 10 meters per second, or big G. It is the constant gravitational pull of the Earth. Constant, depending on where you are, it's close enough. The velocity in the y is going to increase linearly, because for every second of travel, the velocity is going to increase 10 meters per second, so we can see that that's going to be a linear relationship. And the acceleration in the y is going to remain constant, because that's acceleration on Earth is constant. That's the way it is. Let's go to part C of this question. If the projectile's initial speed is 10 meters per second and the cliff's height is 20 meters, how far from the base of the cliff does the projectile land? So, I've written our variables here. AY equals negative 10 meters per second, delta y equals 20 meters, v1y equals 0, delta t equals question mark. So first, this is a kinematics problem. First, we have to figure out what the delta t is. To do that, we're going to deal with this problem as if it was purely a simple up-down, throwing a ball straight up in the air, it's coming back down problem. Because that's what happens, essentially, in the delta y. That's what we saw when we looked at those graphs. That those would look the same for a ball that we had just thrown up in the air. These three at the bottom. So, we can use the equation delta y equals v1y delta t plus 1/2 ay delta t squared. Solve for delta t, and plug in our variables, our a and the y, which is negative 10 meters per second squared, our delta y, and then our ay again. And we get an answer of a delta t of 2 seconds. Now, how far from the cliff does it actually? To find the displacement, the delta x, the projectile has traveled, we can use the time that it took for the projectile to reach the ground from the previous problem and plug that into an equation for the delta x with a constant v. So delta x equals v times delta t. And we know that the velocity is constant in the x, the vx, because that's what part A allowed us to figure out. When we plug those numbers in, we find out that the overall distance that this projectile will travel from the cliff before reaching the ground is 20 meters. Thank you very much.